Hello, and welcome back to my YouTube channel. My name is Professor Govalla, and today I am going to be talking to you about nodal voltage and mesh current analysis methods. To begin, we want to first talk about what a linear circuit is. And essentially, a linear circuit is a circuit composed entirely of independent sources and linear elements. And essentially, a linear circuit is linear if it is passive and exhibit a linear IV relationship. So again, we talked about an equation like Ohm's law, or V is equals to Ri, where the resistor is a linear element. And linear elements have two main characteristics, which are the homogeneous property. The homogeneity property. This is also called the scaling property. And which says that if I have a K and I multiply it by I, this should equals to a K times V over R. So if I'm given a current, no matter how big of a number K is, I can get the same value if I multiply that K by a V over R. And the next property is the superposition principle. And in the next video, you'll see us use this principle to do what we call superposition. And this is also called the additive property. Additivity property. Where if I have a voltage is equals to a resistor, current I1 plus I2, this is equals to, I can distribute that R into I1 plus R2, which is equals to, this would be a RI2, which is equals to V1 plus V2. Some examples of linear elements are a resistor, a capacitor, an inductor, and any linear dependent source. And again, we talked about linear dependent sources. We talked about this can be a current controlled voltage source. This is a current. This could be a current controlled current source or a voltage controlled current source. And this is can be a current controlled voltage source or a voltage controlled voltage source. So these are all linear elements where this is a resistor, capacitor looks like this, and an inductor looks like that. Now let's dive into what is known as the nodal voltage method. And this is sometimes just called nodal analysis. And this is the bread and butter of most electrical engineers when it comes to doing analysis on any circuit. And the key principle of nodal analysis is if you have V1 going into a node, and this is V3, let's say this is VO, this goes down to a V2, and this is connected here to a V4. This is IO. This is an R1, R2, and R3. If you were given a circuit like this and you labeled the currents, you want to label the currents leaving the node you want to find. So I would label this as I1, this is I2, and this as I3. And the idea is that this VO is at a higher potential than V1, VO is at a higher potential than V2, and VO is at a higher potential than V3. When you're given a current source like this, you have no choice but to conclude that the current source is a voltage IO going to VO. And so in order to write my equations, I would first start off by saying VO minus V1 over R1. So again, that's VO minus V1 over R1. And then I add a plus, and then I say VO minus V2 over R3. So VO minus V2 over R3. Over R3. And then plus, erase this, VO minus V3 over R2 minus V3 over R2. And actually what I'll do is I'll change these voltages so it reflects. So this is V2 and this is V3. This would be then R2 and R3. I hope this doesn't confuse anyone. But essentially, what I'm saying is for each of these terms, I'm starting at a VO. I'm subtracting where my current is going to. I'm subtracting that voltage, and I'm dividing it by that resistor. And since the current IO is coming to my terminal, I have no choice but to say minus IO is equals to 0. And this is my equation at this node VO. If you understand this concept, you can really understand how to do nodal analysis for any sets of problem. And we'll do more examples. But again, this is a fundamental method of doing nodal analysis. And essentially, you can solve for VO. You can say VO is 1 over R1, which is this term, plus 1 over R2, which is this term, plus 1 over R3, which is this term. And then you can move, since these are all negatives, you can move them to the left and say this is equals to V1 over R1 plus V2 over R2 plus V3 over R3 plus IO. Depending on what the problem wants you to solve, you can solve for your different voltages and everything. But essentially, this is how I would write a nodal analysis or nodal voltage method for VO. Let's take another example. So in this example that we're given, we're asked to find the voltage through this resistor, VR1, and this resistor, VR5. The first thing we need to do is label our nodes. So I'm going to label this as V1. I'm going to then label this as V2. And then I'm going to label this as V3. And now keep in mind, V3 is automatically 0 because it's connected to ground. And I'm going to label this as V equals to VO. And again, that's given to me as 10 volts. That's my power supply or my power original. And in the problem, they give us the following. They tell us that R1 is equals to 5 ohms, R2 is equals to 2 ohms, R3 is equals to 3 ohms, R4 is equals to 10 ohms, and R5 is equals to 2.5 ohms. So then we can write a nodal analysis for V1. And we could say let me use a different color. We could say at node V1, we can say that our currents are leaving the node. So we could say if you can imagine, this is I2, this going down is I1, and this coming is an I3. Again, these are just my labels. And I could say that I1 plus I2 plus I3 must equal 0. And I1 is basically V1. So I start here. I come over here. I see the next voltage is VO. So I subtract VO over. And then I say over R1 plus R3, simply because R2 plus R3, simply because these two are in series, so I add them up. And then I add a plus, and the conveniencies of this method is you don't deal with any minuses when you're doing with the voltages, only with the currents coming in, as we'll see for node V2. But to continue, V1, so we go to V1 minus V3 over R1. Again, we get that from V1 minus V3 over R1. I hope that makes sense. And then we add V1 minus V2 over R4 is my last voltage analysis, or my last current. And this is equals to 0. To continue, we could say then, so that's equation 1. And then we could say at node V2, we can consider some new currents. We could say that this, in terms of V2 going out, is I4. This is I5, and this here is I6. Again, if you notice, I6 is equals to negative IO. But if we want to write it out, we can say I4 plus I5 plus I6 is equals to 0. And I4, I'll walk you through it again. Again, I4 going this way is this V2 minus V1 over R4. So V2 minus V1 over R4 plus V2. Now remember, this again is V3. So I have a V3 there. V2 minus V3 over R5 plus this I6, which again, I6 is just negative IO equals to 0. And with these two equations, this is the second equation. With these two equations, I can find any parameter in this circuit, which is why nodal analysis is so nice. And what I mean by parameter, it means I can find any current, any voltages through any linear element, through any resistor, basically. So let's go off these two equations and see what we can do. So the first thing we can do is consider that V3 is 0. So we can take all these to 0, both of these to 0. And we can say from 1, we can pull out this V1, and we're left with 1 over R2 plus R3 plus we can pull out this R4, and we can pull out this R1 plus 1 over R1 plus 1 over R4. And in terms of V2, we're left with, let me change colors. We're left with V2 right here. We could say minus 1 over R4 because it's included. V2, which is equals to this value here, which is, we move this to this side, so it'll be plus VO times 1 over R2 plus R3. And then we could say that from 2, I'm going to start again with V1. So V1 is right here. And we could say this is minus 1 over R4 V1 plus, change to red, V2 starts off with an R4. So 1 over R4 plus, this is an R5, 1 over R5 times V2. And then this is equals to, again, there's no VO here, but it's just an I0. So we move the I0 to the right-hand side. If you wanted to, you can, these are just values because we have our resistors. These are just values. So I can say that this is A11 V1 plus A12 V2 is equals to B1, where this is A11, this is A12, this is B1. And then I could also consider A21 V1, this is A21, this is A22, plus A22 V2 is equals to B2, where this is B2. If I plug this into a calculator, so I would get A11 is equals to 0.5 using these values that were given to me up here. I would get A12 is equals to 0.1, A21 is equals to negative 0.1, A22 is equals to 0.5. And B1 is equals to 2 and B2 is equals to 0.8. So when we get that, when we plug this in, we would get 0.5 V1 minus 0.1, sorry, this is a negative, 0.1 V2 is equals to 2, and then negative 0.1 V1 plus 0.5 V2 is equals to 0.8. When you solve this two equations, two unknowns on a calculator or MATLAB, MATLAB or anywhere online, you would get that V1 is equals to V is 4.5 volts and V2 is 2.25 volts. So if you're asked to find the voltage VR1, again, the current the current through R1, so current through I1 is equals to V1 over V3 times R1. It's V1 minus V3 over R1, or V1 over R1, since V3 is just 0. So then we could consider this is 4.5 over, we said R1 was 5, which is then equals to 0.9. Again, this V1 also, VR1 is just equals to V1, by the way, which is 4.5. If you wanted to find the voltage IR5, or the current IR5, or the current through R5, it's just going to be V2 minus 0 over R5. Again, what that looks like is something like this. V2 minus V3 over R5, which is equals to V2 over R5, or 2.5 over R5 was 2.5, which is equals to 1. These are amps. And again, VR5 is equals to V2, which is just 2.5 volts. If you wanted to find the power through R5, if you remember, P is equals to IR5 squared R5, which is equals to 1 amp times 2.5, or 1 amp squared times 2.5, which is 2.5 watts. Or you could use the equation VR5 squared over R, which then equates to 2.5 squared divided by 2.5, which is equals to 2.5 watts as well. So I hope that makes sense in terms of nodal analysis. Again, super simple. You start off at the node you want to find the voltage at. You subtract any nodes. You subtract it from any voltages to the left or to the right or below it or even on top of it. And then divide by the resistors parting them. And then you write out these equations. And you can manipulate these equations to solve for unknowns. And then you find different things like voltages, power, and currents. So now let's dive into the mesh current method. So this is the mesh current method. We refer to this as mesh analysis for short. And again, this is also a very fundamental method that is used across the board in electrical engineering. And we say that a mesh is a loop that encloses no other loop. The current associated with a mesh is a mesh current. So pictorially, what that looks like is if you have a circuit that looks like this, where this is VO, this is R1, this is R2, this is R3. We could say that current is flowing here, IA, and also coming back out as IB and IC, and again, obviously coming back in here as IA. So IA is equals to IC plus IB, and this was KCL from the last videos or 2 videos ago. Again, if you don't remember that, please go check the last 2 videos out. We talk about Kirchhoff current laws, but in mesh current method, we want to say that we can draw 2 loops, 1 and 2, and we can call this I1 and I2. And we want to draw some conclusions or write some equations about I1 and I2 that allows us to then be able to find the voltages across R1, R3, and R2, and the respective currents across these resistors. Okay? So just to reiterate, a mesh current can be thought of as the current flowing through the branches of that mesh, with no regards for the current in neighboring meshes. This does not mean that the current is the same as the actual current flowing through the elements of that mesh. So for example, if I have that this is I1, as you can see, I'm concluding that I1 is flowing through R1 and also I3. But obviously that's not the case because I1 cannot equal IA and IB at the same time, right? So for example, if I say that IA is equals to I1, I must say then that IB is equals to I1 minus I2. And again, that's mainly because if I1 is coming into the element I3 and R3 is leaving the element, then IB is I1 minus I2. So what I'll do is I'll write some clean equations about these meshes so it's easy to understand. And keep in mind when you're writing these loop equations, they have to flow the same way. So the first step is I'm going to write this in the clockwise direction and call it I1, and write this in the clockwise direction and call it I2. It would be wrong if I was doing a problem and I wrote I1 to be in this direction and then wrote I2 to be in this direction. I would get the wrong answer. Okay? So your mesh loop should always go in the same direction. That's the number 1 rule. So I could say that I can write 2 equations. I could say at mesh 1, so here I'm entering this voltage. So when you're writing these equations, you want to put you want to really pay attention to the plus and minus signs. So there's a minus sign here. Let me do a different color. There's a minus sign here and there's a plus sign here. Here, the current is entering, so I'm going to do a plus minus. Here, the current is entering, plus minus, and I'm talking about these currents. So IA is entering this resistor or this element. So plus minus, IC is entering here, plus minus, and IB is entering here, so plus minus. Now, to go back to my equations, since I1 is entering at the negative terminal, I'm going to put a minus V0. And since it's entering at a plus here, I'm going to put a plus R1, I1. And then since it's entering at a plus here, I'm going to put a plus R3, I1 minus I2 is equals to 0. Now, some things that might confuse people is, how did I decide this plus and this minus? And I explained that it depends on the convention I pick my currents to flow. If I pick my currents to flow the other direction, I'm just going to draw a quick 2 blocks. If I pick that IB is going this way and IC is going this way to IA, that's also fine. It would make more sense for me to pick my currents, my mesh to be this way though. And then my voltage would be plus and minus. So this would be plus, minus, plus, minus. And this would be plus, minus, right? And essentially I would get the same answer, okay? So, and you will see in your engineering careers that depending on how a person learns these methods, their written equations, so this is my equation 1, will be different from another person. But you have to know and keep in mind that you must get you get the same answer at the end. So I've always found that most textbooks and most lectures and most professors use the analysis method that I'm teaching here. So if you stick with this analysis method, you should be fine, where we do the meshes in the clockwise direction, and we identify our pluses and minuses in terms of the currents going in. So I hope this makes sense for the first equation. And then at mesh 2, we could say that minus, if we want to start at here, we could say that R3, and we could say I2 minus I1 plus I2 R2. Now again, remember the current is going, so for this situation, for I2, it actually is looking like this, and then for I3 it looks in like that. So it's going into R2 here through the plus, and it's going into R3 here through the plus. So that's why this is plus, and this is plus, and this is plus. And this is equals to 0. Another rule of thumb is that depending on the mesh, if I'm in mesh 1, all my currents at mesh 1, so I1 should be positive. And if I'm in I2, all my currents at I2 should be positive. And anything that is opposing it should be negative. As you see here, this I1 is negative and I2 is negative here. Okay, so now we can write some equations. So it could say from 1, I could say that R1 plus R3. I made a mistake here. This should be R3 plus R3 times I1 minus, so this is this one. So for I2, it's a minus I2, or let me write the R3 first. I2 is equals to VO. I'm just moving this to the other side. And then secondly, from 2, I could say that negative R3, which again is here, negative I1 plus, this is positive R2 plus R3 in terms of this times R2 is equals to 0. So now I have 2 equations and 2 unknowns. And I can go ahead and solve for any type of currents or voltages that I want given these resistor values. So these resistor values were not given in this problem, but if they are given, then I can solve for I1 and I2. And if I solve for I1 and I2, I know the current. I could say that the current through I2, so IR2 is equals to I2, IR1 is equals to I1, and IR3 is equals to I1 minus I2, right? Because they're contradicting each other. So I hope this makes sense. So let's do a final concrete example. Next. So imagine we're given that to find I4, given VO is 18 volts, R1 is 6 ohms, R2 and R3 are 2 ohms, and R4, R5, R6 are equals to 4 ohms. So the very first thing you want to do is draw your meshes. And you want to say that this is a mesh. I'm going to call this I1. This is another mesh. I'm going to call it I2. And this is a third mesh. I'm going to call it I3. So at mesh I1, I'm going to say that this power supply is going to be minus VO. I consider that I1 is going into this R1. So plus I1 R1 plus this I1 is going to this through this I2. So it's going to be a plus. And then it's going to be in, let me actually do my resistors first. So R1 I1 plus R2. The current I1 is going into my resistor, but it's being opposed by this I2 coming out of my resistor. So I need to subtract I2 from it. And then plus R5. And then times I1 minus I3, because again, I1 is going into this R5, but then being opposed by this I3 is equals to 0, and this is my first equation. At mesh, this is I1, I2, I can write that this is R3 because it's going into my I3 times I2. There's nothing opposing it, so it's just I2. And then plus R4 I2 minus, because it's going into I4, but then it's being opposed by this I3 coming out, minus I3 plus R2 times I1, R2 times I2, because it's going into I2 again here, but then being opposed by this I1, so minus I1. And then I say this is equals to 0. And then at mesh I3, we can consider that this is R6 times I3, because it's going into I6, nothing is opposing it, plus R5 times I3 minus I1. I hope this makes sense why this is, plus R4 times I3 minus I2, which is equals to 0. Again, I hope this makes sense why this is, because just to be clear, I3 is going into I4 and it's being opposed by I2. Now, from equation 1, we could say that we can pull out an I1. I'm going to pull out an I1. Or actually, I'll do that at the end. In parentheses, if we pull out an I1, we're left with I1, R2, and R5. So R1 plus R2 plus R5 times I1. And if you notice, for I2, it's a minus. So minus R2 times I2 minus R5 times I3, because it's coming from here. And this is equals to VO, because I'm just moving this to the right-hand side. And then from 2, we get a minus R2 times I1. Again, that's coming from here to minus, plus, and R2 gets all the positive values. So R3, R4, and R2. So I'm going to rewrite this as R2 plus R3 plus R4 times I2 minus this I3 is being multiplied by R4, so minus R4 I3, which is equals to 0. And then last but not least, from 3, we're left with minus R5 I1. This is coming from here, I1, minus R4 I2, again here and here, plus R4 plus R5 plus R6, which is R4, R5, R6, times I3, which is equals to 0. So since we're given these resistance and voltages, we can plug those into here. Right? These are just numbers we could plug in. And when we plug those in, we get 12 I1 minus 2 I2 minus 4 I3 is equals to 18. And minus 2 I1 plus 8 I2 minus 4 I3 is equals to 0. And then minus 4 I1 minus 4 I2 plus 12I3 is equals to 0. That's what happens when we plug our values in. And if you use you can use a 3 equation, 3 unknowns method, or use a calculator, or use an online generator, and you get I1 is equals to 2 amps, I2 is equals to 1 amp, and I3 is equals to 1 amp. That's just algebra and matrices. And to answer the question that was asked at the beginning, the current through I4 is I3 minus I2, which is equals to 1 minus 1, which is equals to 0. So I hope this makes sense, how we generated the currents. And if you wanted to, you could find the different voltages and currents throughout the entire circuit, right? We know that the current through R1, this is just I1. The current through here is I2. The current through here is I3. The current through here is I1 minus I3. The current through here, let me erase some stuff. The current through here is I2 minus I3, which is what we just did down here. And the current through here is I1 minus I2. If you were to ever get a negative value, so for example, if I were to say the current through here, R5, is also I3 minus I1. So if I go down here and I say I5 is equals to I3 minus I1, which is 1 amp minus 3 amps, which is negative 2 amps. This just means that my guess was wrong. This is actually I1 minus I3. Or another way to look at it is that the current I1 is more dominant. So essentially the current going this direction is 2 amps. The current through this resistor is going in this direction, and it's equals to 2 amps. If you wanted to find voltages, obviously V times R, R times I. So the voltage here is I3 times R6. This is I2 times R3. This is R2 times I1 minus I2. This is R5 times I3 minus I1. And this is R4 times I2 minus I3. So again, these methods are very, very important. The nodal analysis and the mesh current. Nodal analysis and the mesh current. And we will be using these all throughout this lecture series. So it's very, very important that we know and we understand them. If you like the YouTube channel, please like, subscribe, and share my YouTube videos. Additionally, if you have any questions on anything in this video, please post down in the comment section, and I'll respond to them as soon as possible. Thank you. Have a wonderful day.